Here's the equation for gravitational field strength in a radial field around some object. And you can see the gravitational field strength is inversely proportional to the square of the distance between the center of masses. If we plot this as a graph, let's say for the Earth, at the very radius of the planet, so measuring from the center, we get a gravitational field strength of 9.81 right there. Okay, and if we double our distance from the center, so in other words, moving another whole radius of the planet away from the surface, then now what we've done is if we double the distance, because of the inverse square law, it's going to be half squared. Okay, so over there, it's going to be half squared, which is a quarter. So doubling our distance quarters the gravitational field strength, so we've got 2.45 there. And if we triple our distance from the center, that's going to be 1 over 3 squared. Okay, so 1 over 3 squared is a ninth. So it's around 1.09 newtons per kilogram. And of course, if we do this for 4 times the distance from the center, then that would be 1 over 4 squared, which is a 16th. Okay, so it's not just gravitational field strength that follows the inverse square law. There's many other examples for like light from a point source like a bulb or a star even. And then you got like gamma radiation emitted from some radioactive source, and anything that spreads out in a spherical manner like this. So as it spreads out, the intensity decreases because the power is being shared over a bigger and bigger area. So if we take, for example, a tiny area over here with capacity, let's say area A, if we double our distance from this point, then actually the area would become 4 times larger. And then if we triple our distance, then the area would become 9 times larger. So as you can see, if that same amount of power is being spread over a big area, then the intensity or the field strength, for example, decreases. So inverse square law says that the magnitude of a force or intensity radiated from a point slash spherical object is inversely proportional to the square of the distance from the center of the source. And we can write like this. In this case, we've got intensity is equal to some constant over the distance from the center squared. But then it could be a force or it can be a gravitational field strength where the K is still a constant. In the case of gravitational field strength, that K is the gravitational constant capital G times the mass of the object in the center. In this example, the table shows the light intensity of a light source at different distances. Determine if the data is consistent with the idea that light intensity follows the inverse square law. So we've got a bulb on the left there is emitting light and is being detected by some light meter, and we want to check it follows this equation here, where if I rearrange this, I've got the intensity times the distance from the center squared, that should equal K, which is a constant. So let's check if that constant is the same for every single data point here. So if we do the intensity squared, times the distance squared, so 12 times 5 centimeters squared. It doesn't matter about the units right now, we're just going to check as long as we use the same units for all of them. That gives us 300, and let's try for the second set of data. So 1.7 times 20 squared, that gives us 680. So already this is quite different. And if we do it for the final set of data, it's 800. So this means that the data, we expect those numbers to be the same, and it's not. So that suggests that the data doesn't follow the inverse square law. Now this is not because the light from a bulb doesn't follow the inverse square law. It's probably because the distance here, it hasn't been measured from the center. So maybe you've measured from the surface of the bulb to the surface light meter here when they've ignored this distance here. So if you put that distance in, maybe it does follow the inverse square law, and it turns out it does. So if we add that distance, which is actually 4 centimeters, and you check it again with 4 centimeters added to each of these distances, it does actually follow the inverse square law. In this example, the data and the table gives the gravitational field strength around Jupiter at different distances from the planet. Describe and explain how the data can be used in a graphical method to determine if the gravitational field strength is inversely proportional to the square of the distance. So graphical method here with the data, it means we need to draw some kind of graph. Okay, so if I plot G against R, which is tempting, I'd get a graph like this. However, this curve could be an exponential decrease, or it could just be a normal inverse relationship, not an inverse square. So it could be any function. So we can't be sure that follows this specific pattern over here. So in order to do that, we have to plot something else. Okay, so I'm going to get rid of this line here. And what I need to do is I need to force this equation into a straight line. That's what I want to check. I want to check for a straight line by plotting the right things on the y and x axes. So if I want to get a straight line, I'm going to compare it to y equals mx plus c. And because we've got k over r squared here, I'm going to simplify this a bit. I'm going to separate it a bit like this, so it's got k times 1 over r squared. And on the y-axis, I can plot g just like how I did before. On the x-axis, instead of plotting r, I'm going to plot 1 over r squared. So now you can see the number in front, actually there's no intercept. This should not give any intercept. It should be going through the origin. If it doesn't go through origin, then you know probably either this data doesn't follow the inverse square law or we've collected the data incorrectly. And the gradient should be a constant, which is k there. Okay, so, and if we test this, we should get a straight line.